Hey, we are Team 10337 Dark Matter, and this is us. We are a second-year FTC team from Mandeville Junior High. This is our robot, BB9. The BB stands for BoxBot, and the 9 comes from our robot last year, K9000. Also, we're all Star Wars fans here. When this year's FTC challenge was released, we started brainstorming ideas for our strategy and robot design. We decided that we wanted our robot to be able to score particles in the center vortex, trigger the beacon buttons, and cap the cat ball. A major part of the robot design was the drivetrain, which Ethan will talk about.
For this year's challenge, we chose a 4-wheel drivetrain for our robot to prevent it from getting stuck. For instance, if a motor burns out, or if one wheel is lifted above the playing floor, our robot is still able to move. Our drivetrain ensures that our robot does not get pinned or pushed around the field by other robots. Also, since our teleop strategy was to score points by shooting particles into the center vortex, we did not want to be pushed out of position while shooting. So we utilized a braking mechanism that the driver can activate to lock the wheels in place. Once we had our drivetrain built, we needed an intake system to collect particles, which Majid will talk about.
For last year's FTC game, we designed and built an intake to pick up particles for the floor competition. The design of the intake system worked well last year, so we decided to use the same design but make some improvements. Last year we used weather stripping attached to PVC pipe. We replaced the weather stripping with surgical tubing because it is sturdier and moves the particles up the intake more efficiently and faster. We used the cardboard backing as a prototype for the intake. After we determined the correct dimensions and shape of the cardboard, we finalized the design by replacing it with polycarbonate. With the intake system working, we needed a way to shoot, which Logan will talk about.
In the beginning of the season, we used a spreadsheet created by Ether, a frequent poster on Chief Delphi, to determine the speed and the angle in which we want to shoot the particles to make them into the center vortex. Based on this information, we prototyped 3 basic shooter designs: a puncher, catapult, and flywheel shooter. Both the catapult and the puncher designs were very accurate, but because of concerns of the likelihood of wear and tear due to moving parts, we decided to go with the flywheel shooter. Once we decided on the flywheel shooter, we had to finalize the design. Emma will share more information with you.
Once we decided we were going to have a flywheel shooter, we started testing different wheels that we already had or borrowed from Mandeville High School's FRC Team 2992. Before we ordered any wheels, we made this spreadsheet. This spreadsheet tells us how big the flywheel needs to be and how fast it needs to spin. We made this spreadsheet so we don't have to order many different wheels. If not, we would have to order different wheels before we find what wheels work. Once we had the right wheels, we tested different configurations. This is our final design. We had 2 flywheels mounted front to back. Once we had these built, we had to test to see if it can successfully get particles into the center vortex. We used a tachometer to see if the wheel was spinning fast enough. We also tested how much tension we need to put on the wheels and how far apart they need to be. Once we have a shooter and an intake system, we need to figure out how to get the particles from the intake system, which Vonnie will talk about.
We had 2 concepts for feeding particles into the flywheel shooter. These concepts were indexing the particles with a belt, which had multiple drawbacks, and using a golden ratio cam wheel. We decided to use the golden ratio cam wheel because with this mechanism, we could avoid jamming and premature shooting of particles. The cam wheel's motions are depicted in the CAD animation on the right. In the CAD animation on the left, you see the particle being transported up and onto polycarbonate sheets that guide the particle till it rests on the cam wheel. The cam wheel pushes the particle up into the flywheel, which then shoots it. You can see this in motion in this video. The particle moves down the polycarbonate and is pushed by the cam wheel into the flywheel. If you focus on the flywheels, you can see that the one at the back is pivoting. That is intentional. In order to accommodate for differences caused by the particle being exposed to wear and tear over time, surgical tubing was used. We have been using this type of feeder since our first scrimmage back in December that was hosted by our school, Mandeville Junior High. Since then, we have competed at 2 qualifiers and 1 regional competition and have made continuous enhancements. Matthew will talk about these additions.
One of the enhancements that we made was the addition of a beacon pusher. This is our original beacon pusher design. It performed very well during autonomous, but we decided to improve it. We changed our design to allow it to pivot so it is able to trigger the beacons at extreme angles. After regionals, we held a scrimmage. During that scrimmage, we discovered a new method to trigger the beacons. If we added a chamfer on the edges of the beacon pusher, it would allow us to deploy it and slide across the beacon buttons to trigger them. This is our final beacon pusher design that you can see us using today. We also added a secondary beacon pusher on the front of our robot to allow us to trigger the beacons while collecting particles against the wall. This is our 100-point autonomous program where we use our beacon slide mechanism. Our robot uses encoders to move and a gyro sensor to turn. It has 2 color sensors. One of them senses the white tape on the floor and one to sense the color of the beacon. We 3D printed a scope for the color sensor so it focuses only on one color. Our autonomous program recorded all robot moves and inputs, which we used to make any needed adjustments to the program. After our first qualifier, we continued to improve our robot by adding an ultrasonic range sensor, which is used to wall follow during autonomous, a limit switch used to control shooter cam, and a lift system, which Arushi will now talk about.
Our cat ball lift contains a form-fitting cradle system that we 3D printed. This helps us pick up the cat ball with more efficiency and accuracy. However, our robot was unable to hold onto the cat ball twice during our second qualifier. To solve this problem, we added an arm to the top of BB9 to come down and stabilize the cat ball. Here's our cat ball lift in action. The lifting arm pivots under the cat ball and is secured by a polycarbonate arm. The driver then moves the cat ball in position for the lift. What makes our cat ball mechanism unique is that instead of going over the center vortex and dropping the cat ball down, it pivots forward to release the ball into the center vortex, which saves time. Throughout this year's FTC season, we've continued to make improvements to our robot. Another thing we strive to continue is to improve our outreach program. So far, we've presented to the community at parks, went on local radio station 94.7 The Lake, made cards for the military, presented to teachers and special needs students, held a robotics pep rally, sold concessions at baseball and basketball games, hosted a free scrimmage, boxed food for the needy, hosted a car wash, including many other events. We will be attending a school board meeting this April and making military care packages. It's been an exciting FTC season and a great learning experience. Good luck on the field.